pretty good. Well, you know, for those of you who worked. But so yeah, it seems like everything is on track with those tests, and there's nothing to worry about there. You can all be calm. Cool. So today we're going to start off with finishing analytical geometry, analytic geometry, and then we're going to move on to eigen decomposition. I just want to start off with this example last week that I've been promising for a while. So this is the equation. Try to bring this thing up. Wait, that's not what I wanted. All right, whatever. There we go. So this up here is the equation for the angle between two vectors. So I thought I would kind of derive it just because I think it can be fairly unintuitive. And so it comes from this setup here. I'm just going to do it in 2D, but you know, everything carries, of course. So we have two different vectors here, V and W. We want to know the angle between them. And so we're going to look at that. So this point A can be written as, you know, it has some XY coordinates up top there. And so we know that that is r cos theta, r sine theta. In this case, r, the radius, is the value b, which I've just given you. And then theta is the actual angle there relative to the x-axis. Okay? Shouldn't be anything too strange, but I'm going to review angles in a second. We do rotation matrices anyway, if anyone's comfy with that. And so what we want to find out is this length of C, right? And so that can come from like high school Pythagoras theorem. Ultimately, what we want to do is we want to get that distance there and that distance there. And so this distance along here is V minus, is the length A, sorry, A is the length of V minus this projection here. So we end up just with what's left. So if you take that, you go A minus B cos theta squared. And then obviously the y-axis is just the y component of this line here. It's just literally like right up to where that goes to. And that is that bit there. That's b sine theta squared. Okay. If we're looking at c squared, you can just drop the square root on the top and you FOIL out all the brackets. You end up with a squared from that term, 2ab cos theta from the multiplication of these two terms twice. And then lastly, you end up with b squared cos theta from this term here. And then from this one on the end, you get b squared sine squared theta. And we can group these two terms here. You factor out the b squared, you get cos squared theta plus sine squared theta, which we know evaluates to 1. Okay, that's just an identity and trig. And so we end up with a squared plus b squared minus 2ab cos theta. All right, a squared is just this line here. That is the norm of v squared. Same with w. B squared is just the norm of w squared. And then lastly, we then just substitute in a and b as the norm of v and the norm of w just by definition, right? That's like from the diagram and the setup. Okay, cos theta. And that is now that distance between the two. That's v minus w. So that's the length of c. Okay. If we then come across and do the more algebraic version with the inner product, if we have the squared norm of that line, we can use the bilinearity of the inner product to just FOIL out the v's and the w's, and we end up with 4 terms. So we end up with v inner product with itself, w inner product with itself, minus v inner product with w, w inner product with v, and then we know that we can collapse this down onto 2 vw inner product. We can kind of swap that order there. Okay, and then as a result, this is the squared norm of v, squared norm of w, minus 2 times that inner product. If we then come in and bring this inequality from the bottom here and drop it right into there, okay, we can end up simplifying and saying, well, we know that these two things must cancel out, these two things must cancel out, and then the minus 2's can be divided away. So what you end up with is the norm of vw is equal to what remains on the right-hand side here, which is the norm of v times the norm of w times cos theta. And if you divide by those norms on the right-hand side, you end up with that equation up there. All right, cos theta is equal to inner product of VW, so inner product of AB instead of VW, divided by their respective norms. Okay, so it's a little bit of an algebraic thing. It's the whole idea is that you do the kind of geometric-y way of looking at it, and then after that you do the kind of inner product linear algebra way, and then you combine the two solutions once you get the two different representations for this component of that triangle, and then you end up with an equation for the difference between them, and then you can simplify that to get an angle between the two vectors. Okay, I'm not going to expect you to do this proof. I just thought I sometimes find it's helpful when there's like this really weird, unintuitive equation like this coming off the top to at least see how you might define it, especially when it comes from like a strategy like thinking in terms of that triangle there in particular. So if this is the only thing you use is this kind of understanding of this triangle and realizing that that can then, by trying to get an equation for C bar over there, you can then come to some interesting equation for this angle between the two, and that's totally fine. That's just the proof strategy. Okay. All right, and then if you remember the example I made last week or the week before, you can then always just bring in the norms, and then you ended up with normalized versions of each of those vectors, which means that the only thing, the intuition there is that the only distance between them, or the only difference between the two vectors, then now that they both have unit norm, is the angle itself, right, or the cos of the angle itself. Okay. There's no questions, and I'll pick up where we left off last week. Okay, we're good. All right. Then last week we just finished with the idea of projections, and we kind of realized eventually we came to the conclusion that the Moe-Penrose pseudo-inverse has this kind of nice relationship. It is actually just the projection onto a line, which minimizes the kind of error. So it is our closest approximation to being able to solve this equation, and what that ends up being is just the closest projection we can get to be, if it's solvable, then the projection itself is the then we can actually project onto B and everything's fine. All right, now what we're going to move on to is an algorithm that comes off of the projection, and it's really useful because a lot of times what we care about is we know that bases are the way we represent space. We've kind of gone through a whole discussion of that, and later in the lecture we're going to talk a little bit about like a really nice, intuitive, useful basis to work in. But in general, we know that all we need is a basis, right? And that's kind of the once we have a basis, we can then do things like manipulations like changes of bases, and then translations and mappings and things like that. But bases in general don't have to be orthogonal. The vectors don't have to be unit norm. They have a bunch of nice properties when they do though. And we might want to say, can I take my kind of ugly, messy basis where if I was doing, if you remember that inner product even, if I'm taking an inner product between two vectors, that ends up being the coefficients in terms of that basis times by this metric A here, where A was that inner product of our basis vectors, right? Things like that. And so if we want, we can now try and orthogonalize our basis vectors so that when I go B times B transpose, I get an identity matrix. And so my norm becomes a lot simpler to compute, for example, would be one of the benefits of having an orthonormal basis. And so that's the whole point, at least one of the uses of Gram-Schmidt orthogonalization, is to take a set of basis vectors that are not orthonormal and turn it into something that is, okay? And in terms of the notation here, we know that our vector space is defined in terms of those basis vectors. So a vector will span or sit somewhere in the span of our basis. But now what we're going to do is we're going to go from the normal ordered basis B to something that's more orthonormal U1 to UN, all right? And the spans will be the same. But again, the way we measure distance and the way our inner products work in the orthonormal case is going to be much more intuitive, okay? And so then there's a second question, is there always going to be such a basis? If I have a non-orthonormal basis, is it always possible to get an orthonormal one so that it's kind of easier? And the answer is yes. You can always, you can always take a non-orthonormal basis and write it in terms of an orthonormal basis. And that's pretty intuitive. If I'm working in 2D space here and I have two basis vectors and this one's really long, this one's really short, and they're not like orthogonal to each other, you can always try and rewrite it in terms of, something that's a lot more intuitive, okay? Sorry, that last one looked a little bad. Okay, and now you have the blue basis, which should be unit length, if I can draw properly, and they're now orthogonal to each other. Okay, so all it is now trying to find a kind of change of basis into an orthonormal basis. And the good news is that there is an algorithm for this, okay, and this is called the Gram-Schmidt orthogonalization algorithm. We're going to walk through it now, and I'll show you an example before we take a break, mainly because I also think this is a good use case of the projection equation, which we derived last week. This obviously uses the projection equation, but I think there's a slightly easier way to write it. So I'm going to kind of kill two birds with one stone there. Okay, so Gram-Schmidt orthogonalization method constructs an orthogonal basis U in the U's from any basis B of some vector space B. All right, and so the way we're going to do this is, and if you bear with me for the notation for 2 minutes, it's actually really intuitive. You're going to just define, and that's what this equals means here. It means that it's true by definition. They're equals by definition of this process. I'm going to define U1 as just being equal to B1. Okay, that's the first step. So whatever my first basis vector is, U1 is just for now going to be the same thing. Okay, step one. Step two is then for every other basis vector in the set, I'm going to come and I'm going to construct a corresponding U vector for it. Okay, so for any K vector in my basis, obviously K is not equal to 1 in this case, I'm going to construct K. All right, and the way I'm going to construct UK. The way I do this is I take BK and I subtract from it the component of BK that lies along all of the previous vectors I've just constructed. So any portion of BK that can be written in terms of a previous U that I've created will now be subtracted from that vector. Okay, and that's what this means. I'm going to now take my new vector BK, my new kind of unorthogonal basis. I'm going to project it with pi. Again, that's that notation we have for projections. I'm going to project it onto the span of all the previous orthonormal basis vectors I've just constructed. Okay, and then I'm going to remove that from BK. I'm going to remove it from itself. What is left is by definition my UK. Okay, I'll show you a visual version of this now. The good news is that we know then that UK will be orthogonal to all other basis vectors I've just created. So we've just now ticked that box. Just by subtracting B being projected onto the span of the previous space, I've now satisfied the orthogonal condition. All right, and so we can then add it to the set, and then we just repeat this process iteratively for all of our n basis vectors. Okay, so we're going to dive into equation 38 now, but let's just finish the bullet points there. So the kth basis vector is projected onto the subspace spanned by the first k minus 1 constructed orthogonal vectors. The projection is then subtracted from BK and yields a new vector UK. This will be orthogonal to the first k minus 1 dimensional subspace spanned by our new basis vectors that we're creating, and then you repeat this process for the n basis vectors. The last thing we need to do, okay, so this equation here satisfies the orthogonal condition. It doesn't satisfy the fact that the U's are now normal. So we always have to, and again, this is a very big place where people lose marks in tests and exams. You need to come through at the end or somewhere in the middle, depends how you want to do it. But once you've done this, you have to then come through and normalize your vector. Okay, in the same way we discussed when we were looking at that cosine equation, whenever you divide a vector by its own norm, its norm after that will now be 1. We know that it will then always be 1. That's called normalizing it. All right, so the norm here will now be equal to UK divided by the norm of UK. We know for a fact that that's going to be 1. Okay, the reason for this is because we define norms in terms of the inner products, and we know that we can pull constants out of the inner product. So in reality, what's happening is we're actually pulling out that denominator. We're actually pulling out what's in the denominator there, so that's 1 over the norm of UK times by the norm of UK. All right, it's not super neat, but I hope you get the gist. All right, you just pull this out front because that's a scalar at that point, and then what you're left with is the norm of UK divided by the norm of UK, which is 1, by definition, always and forever. Okay, so that's the process. Please do not forget to come in through it and normalize your vectors. All right. So here's a visual illustration of what's going on. All right, let's say we're projecting B2 onto B1. Now there is some angle between them. They're not parallel, they're not 90 degrees. So we know that there is some component of the projection that will survive. What we ideally want though is to have these two vectors actually be orthogonal, right? And obviously to be unit length after that. Okay, so step one, we come through and we say U1 is equal to B1. By definition, this is now also U1. Okay, we have that defined there. All right, you can come through now at this point and normalize it. So U1 is equal to U1 divided by the norm of U1. Okay, and that gives us that orange vector over there. All right, usually you want to go U1 hat, keep them separate, but I know I can just see that the notation there at the bottom is just that. So let's keep consistent with the slides. Okay, we are now going to project B2 onto U1. All right. In fact, you're right. They didn't normalize at this point. Okay, they haven't normalized there. I see what's happening. So what we're going to do now is we're going to take B2, project it onto U1, and that gives us the orange vector here. All right. So the component of B2 that lies along the span of U1 after we project it is this orange vector. We are going to remove that from B2. In other words, we're going to shift it that way. The tip of B2 is going to be in the opposite direction because of the negative to its own projection. And we're going to define that as then U2. You can see now that we have two vectors that are 90 degrees to each other. All right. Just by subtracting the projection of B2 onto that first basis vector, we end up with something that's orthogonal. And this will be true in higher dimensions. All right. That's always going to be true. Once we remove whatever part of B2 lies along or is kind of survives that inner product with U1, survives that projection, we'll always know that component of it between the angle here, and we can then just remove it with the subtraction. Okay. And we iterate that for all of our vectors afterwards. Okay. So we'll come through and we'll do this exact same process over and over and over. And then what we want, it's not drawn on the slides here yet, is you then want to take this U1 and you want to normalize it. So we're going to then go U1 hat is equal to U1 divided by the norm of U1. And that'll give us this vector here, let's say. All right, same story. You have U2 defined there, which is again coming from just subtracting the orange vector from B2. You then have U2 is equal to norm of U2, and then we have a vector there. Okay, now they're both 90 degrees and they're both independently normalized. I tend to like normalizing at the end. In theory, you can do it in the middle, which I thought the slides were initially doing here. You can come through at this point when you say U1 is equal to B1 and then normalize it to get U star. You can then do the projection onto the span of U star or U hat. U1 hat, B2. Okay, you see the difference there. Here we're using U1, here we're using U1 hat. You will get to the same answer, right? You're always going to just be removing the components of B2 that lies along this basis vector, regardless of how long that basis vector really is. All right. So you don't have to worry whatever order works. What that means though is that I tend to like doing it as in this way, where you are always just making all of your vectors orthogonal, remove all the components from the previous vectors, and then after that you just normalize them at the end. Once they're 90 degrees, you can normalize them freely. They're not going to interact with each other or do anything silly. Okay. I'm happy to take questions now about that, but I am going to show an example where you have more vectors just now. Yeah.
What is it about the method that you use that you show how you get the basis?
By definition, you start with the basis. Okay.
So, because of the transformation that are applying on that basis.
So you're starting with a minimal set of linearly independent vectors, right? So you're never going to do, none of these operations will add a vector, firstly, because if you start with n vectors, you end up with n, okay? And then secondly, none of them are going to make them collinear, all right? Because you're removing the components of you're removing the component of U1 from B2. There's no way that that's going to like push them to be more in line with each other. And you started with as many vectors as you needed, but no more. And so there's kind of no way of you not having a minimal spanning set by the end of it. Okay. And your question is kind of a good one in the flip side to it, which is if you're not told that the basis vector or that a set of vectors is a minimal spanning set, and you're asked to obtain a orthonormal basis from that set of vectors, then you would first come through and do this thing where you end up stacking a whole bunch of vectors. Let's not use B for it. You'd end up taking a whole bunch of vectors all the way to Vm, and then you would get down into that reduced row echelon form where you don't get a pivot in some column or something, a 0, 0, 0, 0, 0. You know, in this case now, you know that there's only two basis vectors, and then you'll come through and say your basis is V1, V2, and then you do Graham-Schmidt on those vectors. You know what I mean? But the fact that you start with a minimal spanning set means that this will stay a minimal spanning set. Happy? Okay. Yeah, good question. We good? All right. Then the next question is, how do we project onto affine spaces? Is there a way we can extend what we're doing in our vector space onto the affine space? And a reminder is an affine space is just a vector space L that has now been shifted off of the zero vector, right? It's or shifted off of the origin. Okay. Does anyone have any ideas how we might generalize this projection?
Could you maybe like add a bias or remove a bias to that thing so it now sits on the origin?
Correct. That's exactly it. What we're going to do is we're going to first subtract x0 so that you end up with a vector space. You will then do your projection onto that vector space, and then at the end you just come through and add x0 back on. Yeah, well done, dude. There we go. So let L be an affine space. So we have our vector space U plus the support vector x0. Okay, so we define an affine space where x0 is our support vector and U is the vector space of V spanned by some basis V1 and V2. We want to find the orthogonal projection of X onto L now, so onto the this plane that is sitting kind of floating somewhere in our larger ambient space. In order to do this, we transform our problem into an easier context to perform the projection and then undo that original transformation. So we consider the point here where we're subtracting x0 from the vector itself. So we subtract x0 from x as well. We have to remember to do that. Okay. And then now we're working in the vector space, which is our affine space minus the support vector. All right. And now we already know what to do. We already know how to project this vector onto U. Specifically, you just use the vector space projection. And so you end up taking x minus the support point, the support vector, projecting that onto U. And then after that, we just shift it back up. Okay. And you just add back x0. Okay, and so if you're asking, please project something onto an affine space, what you're going to do is just take the point you want to project, subtract the support vector from the affine space, do the projection equation, and it's that like long one with all the bases and stuff. You do that normal vector projection equation, and then afterwards you come back and you add back x0. And those are your 3 steps to projecting onto an affine space. Okay. In reality, what you can also do is, because we know projections are linear mappings, you can FOIL this out. And so it might be somewhat more efficient if you have a lot of data to do it this way, but that's kind of up to you. All right, especially if what you're projecting onto is a much lower dimensional space, getting the projection out the way first without having to do the subtraction helps you. All right, sorry, without having to do the subtraction helps you. But that's a more of a minor computational point. Okay, everyone comfortable with that idea? You guys are struggling today, yeah? Long week. Yeah. Are we all happy? at a high level. We're happy that if we come through and watch the recording of the lecture and look at the slides later on, we're not going to be confused. That's all we need for today. We don't need to fully understand things or be loving life. Okay. All right, let's look at rotation matrices. So a rotation is an automorphism. So we know that an automorphism is some projection called R that maps from, and also just note that this isn't like the R isn't in a real space. Just keep note of how the letters are being written, I guess, or the font. Keep note of the font of the letters. But R, this automorphism, maps from a vector space onto itself. Okay, so it's very particular. We know that in this case, we're not going to be losing rank. All right. In our context, V is typically a Euclidean vector space, and we typically discuss the rotation in terms of an angle around an axis. The angle theta refers to the counterclockwise motion. Okay, so that's pretty common. And so if we have the standard coordinate system in R2 with the corresponding basis E1 and E2, so we have our canonical basis, all right, just it's easy to think of in terms of that. How can we rotate each of these vectors by theta as seen in the diagram below? Well, we're just going to come through and we're going to do what we usually do with rotations from school. We're going to define this angle between the x and the y coordinates, and then this is your hypotenuse. And we know, however you want to remember hypotenuse, what x over r or whatever is, that's up to you. But these are the equations, right? So you have cos of theta is always equal to the x over r, so it's always equal to this distance there, divided by the actual radius of your circle that you're imagining sitting along this line here, okay, forming your triangle. Okay, that forms that 90 degree with respect to the final point, your x-axis and your final point, and so you can then just get the cos of theta angle out of it. The same thing is true for, okay, and then if you want to get your y point, it is the sine of sine theta is equal to y over r, all right? So it's this distance up here divided by your hypotenuse or your radius or whatever. The only tricky thing about this, I think this is easier if you're looking at this one first. This point here can then just be written as, in terms of the xy coordinates, what we just went through. If we're assuming that your radius is units, so the length of your radius is 1, this is what you get to, or just radius is 1, length of your vector would be 1. That's what you come out to. That's fine because this point here is literally what your x point is, that cos theta there and your y theta there. The only way that this gets tricky is when you try to consider this point here, all right, and what's happening with this rotation into the second quadrant, all right? And so there you have to almost be kind of like, you know, turning your, it won't rotate. You have to turn your head kind of sideways, all right? And this is then your x-axis, that is your y-axis for the point of doing this derivation, all right? And that's the only tricky part. Then you have to take note that you're moving in that direction, which is the negative y-axis, okay? So you just need to keep track of like which direction you're actually going relative to how you're forming this triangle up here, okay? It is deceptively tricky. It's the kind of thing that like, it's obvious until you're like put on the spot and then it like falls away or whatever and you get confused. So just keep track that you're forming this triangle with this being the x-axis, that being the y-axis, and that's the radius, okay? In other words, this is the triangle here. Okay. And so in that case, this is the angle that you're looking at. And so you can go negative sine of theta, the negative being just purely from noting that we're moving in the second quadrant. So in the negative y-axis, and then cos of theta will just still be that same point. You're still moving in the positive axis up there. But now your cos and your sine, so your cos is being used for your y coordinate of this vector, and the sine for your x coordinates of that vector. Okay? So just to summarize, you have two triangles, two different angles that are being looked at, or that will be the same angle, but applied relative to two different axes. Okay, so when you're considering this triangle here, to figure out the coordinate of this point, is that angle times cos, that's fine. Cos and x make a lot of sense by our usual equations. There, same for the y-axis over there. So your y point is now with the sine. It is flipped when you get up to the second point here because we're now considering it relative to a different axis. Okay, so in this case, now the cos is determining your y point and the negative sign your x point. Okay, and that, if anyone is, you can then do the usual change of basis equations where you're writing your new basis in terms of your old basis, as we went through on that OneNote at some point. We start in the canonical basis. We're now rewriting our new basis, which is these blue vectors, in terms of our old basis. Okay, so cos of theta times the first one, sine of theta times the second will give you this vector here. Okay, so that's fine. That's exactly what we've spoken through. And then again, it's now sine and cos flipped relative to your first and your second original basis vectors. As normal, then you can come through and you can stack these in a way that writes it as your forward transformation. That's your forward transformation written in terms of your old basis to your new basis. Okay, and when you do that, you get this format here, which is cos on the x on the diagonals, and then minus sine on your off diagonals. Okay, and that is how you derive, or that is the idea of where this derivation of your rotation matrix is coming from. For those of you taking robotics, I'm sure you've seen this a lot by now, but this is the idea of where it's coming from. Is it is actually that change of basis matrix, that forward transform, that's taking us from our original, let's do green, this original green vector here, and this original green vector here. We're now trying to write that forward transformation that takes us to our new basis in blue. Okay, and it's that same method we went through in the OneNote with writing your new basis in terms of your old. Yeah. And so this is exactly what the slides are then saying. And then you can generalize the idea into higher dimensions, where what you're always doing in higher dimensions is holding all of your axes fixed except for two of the dimensions. So in this case, and in most cases, we're only ever going to be rotating two-dimensional planes. All right, everything else is going to be fixed. So when we move to R3, we can rotate any two-dimensional plane about one-dimensional axis, for which there are now three choices depending on which axis we hold fixed. And the easiest way to specify the general rotation matrix is to specify how the images of the standard basis are supposed to be rotated. Okay, while ensuring that they remain orthogonal. What this ultimately just means is that our transformation keeps the one dimension fixed. Okay, our old basis and our new basis stay the same for the fixed axis, and then we're applying the same idea for the other two. Okay. So here the E1 coordinate is fixed and the counterclockwise rotation is performed on the E2, E3 plane. We can do the same idea as we derived on that earlier kind of triangles. If we're now keeping the E2 plane fixed, you have a 1 in the middle. That's obviously saying do not transform that basis vector. But now you have sines and causes in the other coordinates. And again, you always just have to make sure that you're keeping track of whether or not you're moving into the positive or the negative quadrants for any of these. Or in higher dimensions, a quadrant is called an orthant. So which orthant you're moving in, it's like in this kind of very high dimensional gritty box thing. You just need to keep clear which one has the negative. But there's a general equation for this, which I'll show you in a second. Okay, same story. If I'm holding the third basis vector fixed, then you just put the rotation in terms of the other two vectors and all of other two bases. And all of these zeros here mean that the dimension that we're holding fixed also, as much as it is staying fixed, it also doesn't affect the new basis vectors. Okay, so it goes both ways. All right, it's not changing, but it also doesn't affect the new basis. All right, and then you can generalize this into Rn. The generalization of rotations from 2D and 3D to n-dimensional Euclidean space can be described by fixing n minus 2 dimensions and then only rotating around 2 dimensions, the remaining 2 dimensions. This is called a Gibbons rotation. Others do exist, but this is the only one we're going to really consider. And this is the general equation. And the way you can see it is that it is just an identity matrix. Okay, so you can see it has zeros everywhere on the off diagonal, except at the points II, ij, ji, and jj, where I and j are the two axes which we are rotating. Okay, and then that you come in and slot in the causes, the minus sines, the sines, and the cos. relative to, based on that equation there, into your identity matrix, and that's how you get a Gibbons rotation. But the same intuition holds, all right? In terms of if you want to intuit where the sines and causes are coming from, you can imagine this case here, all right? Again, I like that idea that mathematics is about knowing what analogy to hold in your head. If you want to understand a rotation matrix, to me, this is the analogy. This is the change of basis that describes how the sines and the causes emerge in the equation. Then you just come through and drop it into the algebra, which works out, luckily, but then it's just saying everything's an identity except for the two bases that I want to rotate. All right? Identity being, I don't change those bases. What's up?
Almost like above, why is it like that y-axis on the left? Why is that negative sign and not normal sign?
Because if you look in terms of the old bases, right? The old basis vector, the B1 is going that, E1 is going that way in the positive direction. All right. So this axis here, this direction there that we're moving into is now in the negative direction of E1. Okay. And so that's why it's now sine. Well, that's why it's now negative, and then sine because it is that part of our triangle. Okay. Yeah, cool. All right, so rotations have a lot of nice properties, and it follows from them being orthogonal matrices. So orthogonal in the sense that they do not change vectors which were perpendicular, stay perpendicular, and on top of that, they do not stretch or scale any vector in the space. Okay, so they're not adding magnitude to our matrix. So rotations preserve distance, and they also preserve angle. That said, rotation matrices are still not commutative in 3 or more dimensions, so the order of application must be considered. And again, anyone who's done game design or worked in gaming knows that that's a really easy bug, is when you do scale and rotation out of order. Okay, everyone happy with rotation matrices? I'm going quickly, but because I assume that that's somewhat boring. All right. Let's look at an example of the Gram-Schmidt process, and I think this is important. So I'm going to be using this equation for the projection, all right? And as I said, that's not quite the equation that we have in the slides. The one that we have in the slides, I have written down here. Okay? So in the slides, it is written as, let's get you there, and change colors. So in the slides, it's B transpose divided by the norm of B, right? Okay, we come through and we multiply that by x. The thing that I hate about this is that in this case, B is an n by 1, B transpose is a 1 by n, and so we end up with an n by n matrix at the top there, which sucks to work with, right? No one wants to do that. No one has time to do matrix multiplication any more than we have to. Okay, so what I'm going to do instead is I'm going to acknowledge that matrix multiplication with vectors or in general is associative. Okay, not commutative. I can't go x, y is equal to y, x in general for it, but what I can do is change the order of the operations that I apply going left to right to right to left. You guys know what associativity is from your test last week. So what I'm going to do instead is, instead of doing that multiplication first, I'm going to do this multiplication first. Okay, bring that on top. And now, as much as you want to keep the shapes correct, because this is going to end up being a scalar, we know that scalar multiplication with vectors and matrices, that's commutative. So now I can pull this scalar out front, all right? And so now I end up with my full equation at the bottom here, which is get this scalar value, and that scalar value tells me how much of B lies in line with the basis I'm projecting onto. Sorry, how much of X lies in line with the basis I'm projecting onto. So this is essentially like that lambda value that we were finding last week, all right? And so we end up getting then just that multiple of B. But what's nice now is that this is a scalar. The inner product gives you a scalar, or the norm gives you a scalar, and so you end up with scalar multiplication there. Makes it much easier. So let's run that through in this process. Okay. So the Gram-Schmidt process, we know how it works. We first, by definition, say that V1 is equal to U1. Okay. Forgive me for changing notation from the slides. V1 is U1 is our new basis, V1 is our original basis. Okay, then we're going to come through and we're going to say for all of the other vectors, we're going to take the projection of the matrices or the vectors we've already formed. We're going to project our new vector onto that and subtract it from itself. Okay, and the point here and why I wanted to do this example more than just the slides, what the slides offer is because you want to be able to do this for an arbitrary dimension n, right? You don't just want to see the two-dimensional case. But what is good is because we know that all of these vectors are orthogonal, all the UJs are orthogonal, we don't have to take into account each other while we're doing this process, okay? We can just subtract the summation out. This is not generally true, okay? And this is why it is very, very important that we're projecting onto the UJs, all right? And nothing else, because we know that the U's themselves are orthogonal. And so when we project onto that orthogonal basis, we know that we can then just subtract the summation of that. Okay, they're not going to interfere. That's a decoupled projection. That's a decoupled system now. And I think that is, again, that's the kind of thing that gets confusing. It sounds intuitive, but it gets confusing when you put on the spot. Okay, so that's why we can just take this really easy route and subtract the summation of all of the projections. Okay, because they're not going to interact, because once I've projected onto a different basis, we know it's orthogonal to all the others. All right, and then you come through at the end and you normalize your vectors. Okay, let's run through the example. So we're going to do this one at the bottom here. All right, so we're projecting green onto red. Come on. And we want to get an orthonormal basis out of this. So by definition, I'm going to say U1 is equal to 2, 3. Okay. Secondly, I'm going to come through and I'm going to now take out the component of V2 that lies in line with U1, all right, with this vector I just constructed. And so by my earlier derivation, that's just the inner product of U1 and V2 divided by the norm of the U1s. Okay. I think that probably has to be square rooted if I'm, yeah. Oh, no, it's the norm squared. Yes, correct. That's fine. Okay. Turning through that maths, and you can come check me on this later if you want to. That's just the dot product between 2, 3, 1, 1, and then the dot product of 2, 3 itself. I do recommend you check the maths because sometimes I do make mistakes on this. But ultimately now, as I said, the whole point is that this becomes a scalar. That becomes a fraction. That tells you the component of 2, 3 that should be subtracted from 1, 1. Okay, and we do that, and we just subtract, and we end up getting this green vector here. All right, that is now the definition of U2, and that's it. We know that this green vector should be orthogonal to the red vector. Okay, what we have removed, if I can draw this properly, is we came through and we just said, well, what component of this green vector lies along the red, and you drop it down there, and you say that component lies, this vector here in blue is what I need to remove. So I come through and I remove it from the tip of the green vector, and so I get my new green vector out there. Everyone comfortable with what just happened? Okay. And again, we know that if there's more than one vector here, we just do the same process, but now removing them independently, treating them independently, removing it one by one from that red vector. Okay? Yes?
If you have like 3 bases, like working in R3,
yeah,
and then that's orthonormal, like won't you need to do, I guess, this process from each other? Because like if you have, let's say, one of the vectors, like let's say one that's pointing like some in X and some in Z,
yeah.
if you want them, like don't you need to, like what would the process be to get that to be orthonormal as well?
Okay, so let's try to draw it. So the whole point is that because we're projecting onto UJs here, we know that the projections themselves will be orthonormal to whatever came before. Okay, and that means that they don't disrupt each other. But I think what you're asking here is, let's say that there is this then excess dimension there, and we have what color shows up properly on this thing. Let's have that purple there. Okay, let's say we have that vector sitting there. Okay, it's a bit hard to draw it in R3. But what we've now done at this point is we've taken the component of this green vector that lies across the red. I just showed you that. And we now have drawn it out there, right? hovering like slightly off of this plane at the bottom here. So to your point that you just made, what's happened now is I've actually made this green vector slightly more in line with the purple vector, which seems to be a problem. And I think that's what you mean by they're interacting. What I'm going to then come through and do, though, is I'm going to then take the purple vector when I do the next step. Let's get to purple again. I'm going to take the purple vector and I'm going to subtract from it the component that lies along red and the component that lies along green. And I'm going to end up sitting with something like that. Okay, so because I'm doing it recursively, one step at a time, and I know that the vector I'm constructing now is orthogonal to all of the basis vectors that came before, I know that when I get to the end of this, my last vector is going to be orthogonal to all of them. Okay, and then for the second last one, it was orthogonal to all the ones that came before it. And so we know that that will then work out algorithmically. Okay, by the end of it, it will converge on that orthonormal basis. And then the reason why when I'm doing a new basis vector, like when I'm doing the purple case here, I'm not interrupting any of my previous vectors is because I have by definition made all those previous vectors I project onto orthogonal as well. So again, your question's correct. This approach where I treat them independently is purely because I'm projecting onto an orthogonal basis of vectors that came before.
So like now if you just go a little bit to the right, like what would the inner product be like here with U1, U2,
yeah,
like the third dimension?
Okay, so let's say we're doing a U3 thing. I'll just write out the equation here. So U3 will be, so then hypothetically U3 would be equal to V3 minus the inner product of U1, V3, U1, U1, minus the inner product of U2, V3, U2, U2.
Thank you.
No worries. Okay. So it's just that application of that algorithm repeatedly, and then this is kind of what I was saying with that summation, is that bit at the end there. Okay. Let me try and write this neater, and then I'll leave it on the slide. I need to re-upload this one anyway. Minus 2. Okay. And then on the right here, I just came through and I did the exact same calculation in terms of the way the slides do it, just to demonstrate that you get to the same answer, and you get to 3 minus 2, 1 over 13, and here you get 3 minus 2, 1 over 13. You can check me on that again, but it's just the exact same, ultimately the exact same thing. You just do the multiplication in a different order. But again, here you get to a square matrix 4669. All right, which I just prefer not to get. But it's up to you which version you use. You will be marked correct either way. And then lastly, do not forget to come through and normalize your vectors. All right. And again, you're taking these vectors. You're taking this projected value here, and then obviously 2, 3 was what you were given at the start. But make sure you're using your final vector to normalize it. All right. All right. That's what gets stuck in there and stuck in there. Or rather stuck in there. All right, everyone comfy that they can do Gram-Schmidt orthogonalization? What's up?
Your minus
My minus got swallowed up. Thanks. Good catch. Nice, thank you. All right, we good? Sweet. Let's take a 15-minute break. I'll see you at 20 past 3, and we can move on to matrix decomposition. Guys online, can you hear me? Great, thank you. All right, you guys ready to get started? Okay. Let's look at some matrix decomposition now. So we've done analytic geometry and linear algebra. We can now get to one of the major applications of this whole thing and one of the greatest kind of successes of linear algebra, which is matrix decomposition. So at its core, this is the idea that we want to re-express an original matrix into a number of subcomponents or parts, typically in the form of a matrix product or weighted sum of matrices. And the re-expression typically exposes fundamental aspects of the original matrix in a more direct manner. In my case, I like viewing a lot of these matrix decompositions, particularly eigendecomposition, singular value decomposition, as a change of basis. And that's why I yarned on for a month on change of basis, is because ultimately singular value decomposition, these really complicated, typically unintuitive concepts, I find fall out if you look at a change of basis and why you might care. And the whole point of why eigendecomposition and singular value decomposition is good from that perspective is that is the basis that gives you 1D systems. So if I start with one n by n system, so one big n by n matrix, the eigendecomposition is the change of basis that gives me n one-dimensional systems. Okay, it decouples the system is the phrasing. And so that's why I care. That's why I think those decompositions are really important. Those two in particular. There are others which makes things a lot more computable, for example, and they all have their own properties. And so matrix decomposition is a broader concept, but in general, in any class that you've probably done, those have been the big ones, and that is why. Is because this ability to decouple a system makes it solvable. Okay, in almost all further levels of maths. Right, you're going to go into numerical optimization, all those sorts of things. That's why. Okay, at the very least, something like squaring a matrix is really hard until you decouple it into n 1D systems, and there's just your 1D systems to the power of n. That now it's very easy to work with. So that's the whole idea. The simplest example of a concept of this kind of decomposition comes from your natural numbers, and so we know that we can always rewrite a natural number as a product of primes, and so you can end up, for example, with the number 24. Can end up with 24 rewritten as a product of primes, so 2 to the power of 3 times 3, that is really large, is one kind of decomposition into decomposition of your primes into primes. Okay, so here's the textbook's like kind of outline of these concepts. What we're going to mainly be talking about today is eigendecomposition and a little bit of, we're going to be talking about the determinants, invertibility, and the eigendecomposition. We'll chat about SVD and diagonalizability and all of that next time. But let's start by looking at the determinants. So determinants are only defined for square matrices. If you don't have a square matrix, you can't get the determinant of it. And it's denoted for a matrix A in this form. So it's literally just the det and then in round brackets. Or you can write your matrix, but now written with straight lines instead of actually as a matrix form. And so what this does is it tells you how this mapping A, how it transforms space. So it will take a value, a matrix that's n by n, and map it to a single real number. Okay. And so before we define how to calculate the determinant, the applications are worth briefly exploring, and then I'll chat a little bit about the intuition of it. So recall from chapter 2 that in the case of a 2 by 2 matrix, we can get an explicit formula for an inverse as follows. So for a 2 by 2 matrix A, the inverse is just the product of its diagonals minus the product of its off diagonals. That will give you a fraction up front. And then you just swap the diagonal terms over there, and then you put a negative on the off diagonals, and you keep that in matrix form. Okay, that will give you the inverse matrix. Again, this only exists if this value at the bottom here is not 0, right? If it is 0, you're just dividing by 0, which we know doesn't work, right? That's not defined. And so this denominator is in fact the determinant of a 2 by 2 matrix, the determinants of A. So what this means is that the inverse of a 2 by 2 matrix exists if and only if the determinant of A is not 0. Does anyone have any intuition for what this means at this point if the determinant is 0? when we were speaking about invertibility, right, think about what we were saying. We were saying that we always need to be able to bring our data points back to the original space. If I've done a mapping that has a 0 determinant, what's happened?
You've lost rank.
Exactly, you've lost rank. So if I had data points sitting in a square, I lost rank, so I have to project them onto a line. Now, I don't know whether this data point that was here came from any point lying across that line, let's say. That line got mapped to a single point, which means I lost rank. The determinant has a more general concept. Thank you for that. The determinant has a more general concept as well. The determinant is the change, so it depends on what dimension you start in, but if you're working in 2D, it is the change in area that results from applying a projection, right? So again, if I'm starting with this square here, and I am applying a mapping A, and I get this square here, all right, 2 doubles the size in both directions, I have now 2 to the power of 2, so 4 times my area. That is what my determinant will tell me. Okay, same for a cube. If I'm operating 3D, it tells me the change in volume, and then, you know, in higher dimensions, you know, hypervolume or whatever it's called. Okay, so it is the combined stretch in the space itself across all dimensions that results from applying a mapping. And again, if my combined stretch is 0, if I've stretched something in a way that gives me a 0, it means I've lost rank. I've lost a dimension. Okay. In that sense, my volume, if I started in 2D, my area became 0. I sit on a line. If I started in a cube, I've gone to a square. I had volume. I now only have area. So my volume is 0. Okay. So theorem 4.1 says that for any square matrix that is an n by n matrix, it holds that A is invertible if and only if the determinant is not 0. You can directly obtain the inverse for a bunch of them up to maybe 3 dimensions with relative ease. So the determinant of a scalar is just the value itself. So again, you can't divide by 0. So if that value itself is 0, then you can't invert with it. We just looked at the n equals 2 case, and then there's n equals 3 cases called Cyrus's rule. It's just a very long equation written out like that. But what it ultimately comes down to is doing the usual version of computing the determinant that you guys know, which is where you'll kind of cancel out a row and then write out the submatrices multiplied by one of these terms up here, okay, as you go. And that gives you your first term there. I'll go through this equation or this formula or algorithm now. Okay, but just so everyone's comfy, this equation will give you this. All right, so this algorithm we're going to come to compute the general determinant with the submatrices. It's the same as Cyrus's rule in 3D. But if you feel the need to memorize that so you can compute 3-dimensional determinants, go nuts. One of the nice things about determinants is that they work really, really well in special cases. And one of these special cases is when you have a triangular matrix. So a triangular matrix, it's an upper triangle matrix if all elements, it's an upper triangle matrix if all elements lie above or on the diagonal. In other words, the elements of Tij are equal to 0 for I greater than j. Okay? All right, so we know that when I is equal to j, we're on the diagonal. So when our rows is larger than what the corresponding column we're looking at is, then we're going to get a 0. Okay, so in this case, I is 2, for column j is 1, so you stick a 0 in there, and so on. All right, it's a lower triangular if the opposite is true, if you're looking at the top elements. Okay, so in this case, the row is 1, column is 2, so you stuck a 0 in there. Now that's a lower triangle matrix. All right, pretty visually intuitive. What is nice about a determinant is in this case, if you follow the rule, it'll fall out, but you can also remember it, is the fact that the determinant of a triangular matrix, be it upper triangular or lower triangular, is just the product of its diagonals. Okay? In this sense, you just come through and you multiply those terms together, or those terms together. You will get the determinant. Okay. However, if it's not triangular, and I mean, one method is then to rewrite it in triangular form, you get it into row echelon form, then you'll get an upper triangle. Okay. But if it's not, and you don't want to do row echelon form, then you can just do a generalized algorithm. And the most common version of this is called Laplace expansion. and it's another recursive algorithm similar to the basis orthogonalization algorithm we just looked at. Okay, so the same idea holds. You're going to come through and you're just going to recursively do these updates and treat it kind of a subcomponent of the problem one after each other. Okay, and it's what I just showed you. So let's see if there's an example here. So we have the matrix A, right? And so what we're going to do is we're going to expand across one of the rows or one of the columns. I'll show you the general equation now, but let's look at the example. So what you're going to say is look at the row and column indices. Okay, so in this case, this is the first row, first column. So that's 1 plus 1. You're going to raise the number minus 1 to that power. Okay. Similarly, when we're considering this element here, and I'm just expanding along the first row in this case, you're going to say that that is the first row, second column, 1 plus 2, and you raise the minus 1 to that power. What this will essentially give you is that checkerboard that looks like this. So this is positive, negative, positive, negative, positive, negative, positive, negative, positive. Okay? That is that term that you add in the front, all right? Whether or not it's positive or negative follows this pattern out front here, but it actually comes from being able to just say minus 1 raised to that power. Okay, so that's step 1, is you get that the sign off the front. Then you're going to take the coefficient or the kind of value of the element that you're of the row that you're running across. So in this case, 1, 2, and 3 are your coefficients out front. So 1, 2, and 3 out front there. And for every single one of those values, you're going to consider the submatrix that happens when you delete its row and its column. Okay, so the first row, first column, that is our coefficient. That's the 1 off the top. You're deleting its row and its column. What remains is its matrix that you're going to now look at, and I call it the submatrix. All right, so that's 1, 2, 0, 1, 1, 2, 0, 1. Okay, same story for the second element. I'm now going to multiply by that. That's my multiple off the front. And I'm going to now consider the submatrix that results when I delete its row and its column. And so we end with 3, 0, 2, 1. We have 3, 0, 2, 1. All right, same story at the end here. 3 is my multiple, delete its row, delete its column. 3, 1, 0, 0, 3, 1, 0, 0. Okay, why this is now recursive is because I have now just gotten 1, 2, 3 new determinants. Okay, which I now need to solve. But those are two-dimensional determinants, and so we can apply that kind of earlier rule that we know how to work with. At this point, this is just an easy enough computation to do. Okay. So now we come through and we say diagonal minus the off diagonal, so that's just 1 minus 0 there. The diagonal here minus the off diagonal, that's just 3 minus 0. And then here we get 3 times 0 minus 1 times 0, so that's 0. Keeping track of the signs also out front. So in this case, because this is 1, 1, so that's minus 1 raised to the power of 2. That was a positive 1. In this case, this became a negative, and our multiple is 2, so negative 2. And then in this case, it was once again minus 1 raised to the power of 4, which is 1 plus 3. So we get a positive, and the multiple was 3. Okay, so those are 3 pieces, and then you just solve that addition, that kind of addition problem. Right, we get minus 5 in this case. What does the minus sign in this case represent? If 5 is the fact that my volume is increasing by 5 in this case, what would a negative be? What does it mean? Like why? What about the direction?
It's enclosed.
There we go. It's going to cross 0. So if I had a box sitting in the first wall tank, whatever it is in 3D, it's now going to cross that line and jump to another wall tank. Okay. So here is the general equation. You can expand along any row and any column, so you don't have to do this process using these as your scalars out front. You can use any of these, all right? And for someone who is probably paying attention, there is a very easy one, which is these zeros up front here, which means that we would, in this case, probably want to expand along the last row. And if you do that, you don't have to solve 3 small determinants at the end. You just do 1, because you know that those are going to cancel out front anyway, all right? And so then in that case, you just come through and say, well, this is row 3, column 3, so that's my multiple on my scalar. and then 1 was my actual scalar, and then if I delete row 3, column 3, I'm left with the submatrix 1, 3, 2, 1, 1, 3, 2, 1, or 1, 2, 3, 1. Okay, then you do the diagonals minus the off diagonals, so 1 minus 6, and you get minus 5. Same answer, but much easier to compute. All right, so I would recommend that you be kind of smart for yourselves when you're doing these computations. But the same story holds, all right, it is the summation, all right, where the sum is the number of rows or columns we have in our matrix. Again, it's square, so it's always going to be n for an n-dimensional matrix, n by n matrix. But for every single row or column, you're doing one of these things. Okay, so that's what the summation is indicating. We have 3 columns here, so we get 3 of these terms to solve. All right, so that's the summation coming through. And then we're saying that what for each of those terms inside the summation, we're solving for the sign out front. We're going to take that scalar multiple coming from the row and column that we're expanding along, and then we're going to take the determinant of the submatrix that remains. Okay, you can see that the notation here, AKJ, is the submatrix of A that we obtain when we delete row K and J. It's always going to be 1 dimension less. Okay, you can do it for a row as well if you want. Is everyone comfy that they can compute a determinant? Yeah.
Can you please explain again what the negative 5 means that you mentioned that?
Yeah. So let's look at this in 2D. So if I'm starting with this square here, all right, and let's say my determinant, I have some mapping A, all right, then what A is going to do in this case, okay, so I have some mapping A, and the determinant of A is equal to, let's just say, -1. What it's going to do is going to take the exact same square, the area will stay the same, but it'll now be sitting on the other side. Cool. That's determinants. There are a number of really useful properties to these. Okay, so if we let A and B be 2 n-dimensional vectors, matrices, then the determinant of their product is the same as the product of their determinants. That's this first property. This one is used a lot. It's a very powerful. It's a very powerful law. And ultimately, what it kind of means is that, again, if I'm applying 2 transformations to my space and they're both kind of keeping me in that same, without losing rank, or if either one of them lose ranks, then it doesn't matter. But essentially, I'm doing 2 transformations to my space, one on top of each other. The net transformation is going to be, or the net kind of expanding of the space is just equal to the individual expansions that they do. If one expands and one contracts, if A expands and B contracts, then we can just take the product and we'll get the net expansion from both of them. Okay? Similarly, the determinant of A is equal to the determinant of its own transpose. And then if A is regular in that it can be inverted, then the determinant of A is just the determinant of the inverse is 1 over the determinant of A itself. Okay? This is another really nice one, because what this is essentially saying is if we combine this with the first property, then what we get is determinant of A inverse is equal to the determinant of A times by the determinant of A inverse, which is equal to determinant of A divided by the determinant of A, which is equal to 1. In other words, if I apply a mapping and then I invert it immediately, so I get back to my own space, what's happened is that I haven't expanded or contracted that space at all. Yeah.
You have to have their own determinant in order for it to be invertible.
Correct. A is regular.
Yeah.
That is an assumption of it, yes. Okay. That's nice. That checks out. At least those 2 properties combined give us something intuitive, which says that if I apply a matrix mapping and then I invert it immediately afterwards, my net change in transformation is 1. My volume has stayed the same. Okay. If A and B are similar matrices, then the determinant of A and the determinant of B are equal. And this means that the determinant is invariant to the choice of basis of a linear mapping. Okay? Remember when we were talking about those equivalent mappings, and we were saying that there was this mapping, if I start with, I have to go to a smaller pen. If I start with basis B, and I can go to B tilde, and suddenly I have basis C, and I can go to C tilde. Okay? I can do those change of bases back and forward. If I then also have the mapping A from there, I wanted to get the equivalent mapping A tilde, right? Okay, and we said that those were called similar matrices if A and A tilde were just two representations, but B and C were in the same dimension, right? If we were doing the transformation in a different, doing transformations but into the same kind of ambient space, then in that case, this was how we wrote our similar matrices. And so what this is saying is whether I take the determinant with respect to A or A tilde, I get the same result. Okay, that's really important. The amount of stretch that my transformation does to my space does not depend on how I represent that space. Okay, it does not depend on the basis chosen. Okay. Okay, and then adding a multiple of a row or column to another one does not change the determinants. Again, we can do row echelon form, and all you're doing there, we know that actually that's also a change of basis. So from the previous point, that doesn't change it. Now, another important point is if we're applying a lambda to A and then taking the determinant, that is the same as pulling out lambda, but we have to raise it to the power of n. Okay, then do the determinant of A. And that's that same story. If I start with a cube and I'm now scaling the way I transform the space, what I'm doing is I'm saying instead of being, like doubling the space, I'm now quadrupling the space. But it's along each dimension, right? So the volume has now increased. But it's not it's not increasing double, it's increasing 2 by 2 by 2 in 3D, right? So that's why we have to raise it to the power of the number of dimensions we have. And that's the whole point of the determinant, because it's talking about area or volume. It's the power of the dimension that's being worked on. Okay. Also, you can derive this similarity property using the first, this property and this property, just as a sanity check. Let's do that. So if I have this matrix A and I've written in terms of two different change of bases, so S and S inverse is the change of bases, B being the equivalent transformation, then when I write out the determinant of all three of them, I can use the first property to say, well, I'm just going to separate all three of them out. Now I get the determinant of S inverse, the determinant of S, and so then we use the second property here. We know that determinant of S inverse is actually just the determinant of S, 1 over the determinant of S. So I have 1 over K and K, and so when we cancel out, what we end up with is saying that the determinant of A is just the determinant of B. All right, that's a little informal proof. Not informal, it works, but that's like a little quick proof to show that those determinants are equal. Okay, and then lastly, swapping two rows and columns changes the sign of the determinant of A. Because of the last two properties, we can use Gaussian elimination to compute the determinant by bringing A into row echelon form. But again, if you're going to swap those two rows and columns, you just need to be careful that you're not flipping signs, okay? Because swapping those rows and columns corresponds to also changing the orientation of your orthants in a high dimensional space or your quadrants in 2D space, right? So again, it might look then like it's crossing a boundary. Okay, those are the properties of your determinant, but the main ones that matter are the first, the third, and then this one for the inverse, and then that one there. Okay. Another concept that comes up, and I found the trace to be somewhat less geometrically intuitive. If everyone has a good geometric interpretation of the trace, do shout. But the trace can also only be, well, it can be generalized to non-square matrices in this case. But considering the trace of a square matrix, it is just defined as the sum of the elements of its diagonal. Okay. In the sense, the elements of the diagonal of a mapping A are the amounts of stretch that are aligned to the original axis, the original basis. So in this case, it's just the sum of the original stretches that are being applied. The trace satisfies the following property. The trace of the sum of two matrices is equal to the sum of the two traces. That should be pretty obvious, because if I, just have this here plus BII, that's a sum of a sum. You can obviously just take that sum in. Okay, that is because summation is a linear operator. Okay, if I'm scaling A, then that's the same as pulling out A out front. So the trace of the scaling is equal to the scaling of the trace. And again, in this case, because it's a summation of my stretches and not the product of my stretches, you don't have to take into account the power of the transformation. Okay, the trace of the n-dimensional identity matrix, denoted like that, is just n. So again, that will just tell you the number of dimensions that you're embedded in. And then lastly, the trace of a matrix AB is equal to the trace of BA. All right, you have to flip the order so that these two elements still fit next to each other when you do the product. But that is quite a remarkable one, and I must be honest, I don't have a good geometric interpretation for why this works. Okay, the reason is just because then at that point the diagonal becomes the coupling of the system kind of doesn't matter to the trace, and so that's what that product is kind of taking into account. The reason why most things in matrix multiplication aren't commutative in this way is because you need to take into account the order of those couplings, whereas in the trace it's just always going to be the diagonal. The diagonal's the same either way. You can write it out in matrix multiplication form if you care to, but yeah, I don't really know if there's a very good geometric interpretation for that. It's just a cool algebraic finding. Okay, it can be shown that only one function satisfies these four properties together, and that is the trace. And there's a citation there for anyone who wants to read the paper. The fourth property then also generalizes to invariances under cycle permutations. So if I have more than one matrix, I can actually just keep cycling these along, and obviously the one on the end comes forward there to the front. But you can keep doing the cycle, and you'll then obviously be able to then realign your matrix multiplication, sometimes in a way that makes it really efficient to compute the trace. One example of this is if I have an outer product, so x times y, in this case x is a row, or x is a normal vector, a normal column vector, and then your y would be some kind of row vector. That's going to give you a 2 by 2 in the case above, but in general you'll get an n by n. If I come through, then I'm going to have to add together a bunch of terms. In that case, it'll give me 2 terms to add. Or you can use the cycle permutation, where you just keep moving the matrices one element to the right, and then the one on the end comes to the front again. You cycle along. You can do that to now actually write this as xy transpose becomes y transpose x, but that's now a normal dot product. So an outer product has now become an inner product, and so in this case you just get a scalar, and the trace of a scalar is a scalar. Okay, so this is a bit neat, a bit of a neat property, which kind of shows that the inner product is also representing fundamental about stretches in space. Okay, and it goes back to the example I showed you at the end of last week, where you can think of a row vector as being some measure of distance and how many lines that a normal column vector is intersecting in the direction of that row vector. Okay, so the dot product is actually doing something geometrically intuitive, and the trace can kind of expose that fact. You can also use this to show that similar matrices will have the same trace regardless of the basis, and so it's nice that your trace is independent of the basis that you define it in. In this case, again, we substitute in for B, change the similar matrix definition, and now we use that cycle invariance to take that S over to the end, and now we get ASS inverse, and you get the trace of A. Cool. So again, this means the trace does not depend on the basis. I always wonder if they teed up the notation in this example so that he wrote as. Because he writes it backwards earlier. It's actually B and A are swapped in the earlier example. I'm always like, is this deliberate? Okay. So that's the determinant and the trace. Again, I think the determinant is the thing that has a lot of geometric intuition, and it's the thing that will come up in a right now. But I guess the trace algebraically is a very neat operator, and there's often times where the trace is a very useful thing. Okay, are we all comfy so far? All right, a lot of definitions today. Okay, we're going to now look at the characteristic polynomial. And again, this is something that you kind of use to define and tee up eigendecomposition, but in reality, the algorithm that you use to solve it, you never actually just write it out this way, at least I don't. One of the reasons, because I actually also don't know what the exact geometric interpretation of a characteristic polynomial is. There are cases where like the C0 in the characteristic polynomial is the determinant of the matrix itself, and that's nice. That's a kind of good property of the characteristic polynomial to fall out. And then all of these other terms here are your coefficients that will take a full rank determinant A and make them non-full rank. You know what I mean? So this is kind of like the idea of what we're about to solve for with this characteristic polynomial is we're going to try and pick lambdas that take something that is full rank, the original C0, and find a way to get it to be equal to 0 by just picking lambda values. But in reality, again, the trace to me doesn't have a ton of geometric meaning, so I don't know how to interpret the rest of this geometrically. Again, I'm always keen if anyone has ideas. But the kind of whole point, at least the way that I see the characteristic polynomial, is the thing that I just described, which is to say, here is C0. C0 describes the determinant of a matrix A. Matrix A is full rank. Hopefully we're not getting a 0 up front there. But now our lambda values, how are we going to pick the lambdas that get us a 0 determinant? How do we pick lambdas so that we lose rank? All right, and that's the whole idea of eigendecomposition that's coming up. But let's just get through the definition of this characteristic polynomial. So if we have a square matrix A, what we're going to do is we're going to take the identity matrix multiplied by some value lambda. We're going to subtract it from A, and we're going to take that matrix and get the determinant. Okay, and what falls out from that is this equation here, where we get increasing powers of lambda all the way up to n. Again, we should get n to be the dimension of our matrix. A is typically going to be full rank. Okay, and then the C0 to Cn minus 1 is the it's called those coefficients are the define the characteristic polynomial of A. All right, and in particular, C0 is intuitive. It's the determinant of the matrix independently, and then all your other Cn's have this kind of property up front here, where they're taking into account the sign, and then they're just the trace of A. All right, so that's the algebraic definition of it, but let's kind of look at where this gets us and the intuition for why we might want to compute something like this. Okay, and that is to get, firstly, your eigenvalues and your eigenvectors. All right, and so let A be an n by n square matrix, and then lambda is an eigenvalue of A, and x, which is going to be embedded in Rn, and it's not going to be our 0 vector, is the corresponding eigenvector of A if the following holds. Okay, we call that the eigenvalue equation. And so what this is essentially saying, right, is if I take some vector x and I multiply A by that value x, right, the ultimate thing that I get V will just be the same as applying a multiple. Right. So for example, if I'm in a 2D space here, and I have some vector x, and I apply a mapping A to it, A can only stretch the vector if it's an eigenvector. In other words, x lies along a plane that is orthogonal to all except one of the dimensions of influence of A. Okay, it lies in a direction where A is just stretching. It's not doing any rotation. And again, what that means is that in that direction, there is no coupling in the system. That direction acts in one dimensions. It will only stretch. Okay? And so that is a particularly useful property, because what that means is now I can abstract away what is a really difficult computation, which is a matrix times by x. And again, that is usually going to be taking into account multiple dimensions of influence. and say, well, actually, it just corresponds to me stretching x by some interpretable value. All right? There is no coupling in the direction of x. That is the key point here. And that is the key insight of why we solve for this. Okay? For the eigenvalues, the following, and eigenvectors, the following important statements are equivalent. Lambda is an eigenvalue of A. We've just said that. There exists an x in Rn excluding 0, such that that holds, such that the eigenvalue equation holds. That's the same. Importantly, if I take lambda, multiply by the identity matrix, and subtract it from A, I will lose rank. Okay? That's another important perspective of this. This is not always going to be true. If it's another vector that I'm doing this on, what we might be doing is manipulating two different axes of influence at once, but not in a way that gets me to a 0 on either of them. You know what I mean? I might be taking my square and stretching it this way, but it's not going to collapse onto a plane. All right? Only when it's an eigenvector does it collapse onto a plane, and that's because I'm now removing its ability to stretch. I'm essentially taking this stretch dimension that x would be pointing in, that A would be stretching along, and I'm making sure that it can only set things to 0 in that axis. That's what happens when I take lambda times by the identity in that case. All right? And similarly, what that means is because now I've lost rank, my determinant is now going to be 0. Okay? The whole point that what we're trying to solve for is which directions does this mapping stretch in, such that when I remove that stretch, I cannot invert the problem anymore. All right, such that I lose rank. Okay, and you can derive these two properties from this equation up top here, and I do a little thing on the right here, but I'm sure you guys can all already see it. So firstly, we take our eigenvalue equation, switch colors, and we just note that lambda x is the same as lambda times I of x. Okay, then we take that over the equation, and we now factor out the x. Okay, luckily matrix multiplication is linear. Again, that is the whole point of this field, and it's kind of why it keeps coming up, is the fact that this matrix multiplication is a linear operator, so we can factor out those x's and stuff like that. Okay, linear algebra, that's why it's called this. All right, and so ultimately now you will identify this as a homogeneous system of equations. And so you can come along and you can do the usual A minus lambda I, drop your line there, and 0, and you solve for that. Okay, you get the general solution. The general solution, any vector lying on that line is an eigenvector. Okay. All right, so this gets us to the point of collinearity and codirection. Okay. Two vectors that point in the same direction are called codirected. Okay, point in the same direction, codirected. Two vectors are collinear if they point in the same or the opposite direction. So it's again a little bit more of a general term. If it's parallel to another vector, but it's just in the opposite direction, now it's collinear. They still lie on the same line. Okay, and so this is one important point of an eigenvector decomposition, and it differs from the singular value decomposition, is that the eigenvectors are not unique. In other words, if I have x and it's an eigenvector of A, so again, applying A to x is just the same as stretching in that direction, that is associated with an eigenvalue lambda, then for any C scaling, aside from setting it to 0, of course, it holds that C times x is also an eigenvector of A with the same eigenvalue. All right, so there's a little informal proof here. If I scale my eigenvector by a multiple C, then we know that, again, because matrix multiplication is a linear operator, I can pull out the constant up front. And then we now are back to a case where I can apply my eigenvalue equation. And so I get lambda times x. And then now I can just swap my two scalars. In that case, that is commutative. And so it's the same then as saying, well, I have my original eigenvector there, and my lambda is written out front. And so these two terms, that is the eigenvalue equation, where now Cx is my eigenvector, all right? Not here, where just x is my eigenvector, all right? And again, sometimes if you're proving things this doesn't seem necessary, but getting back to Cx on either side, that kind of completes the proof. You know, these two things together now show that it's the eigenvalue equation. All right. And in this case, thus all vectors that are collinear to X are also eigenvectors. Collinear because C is an element of the reals, so it can be negative, in which case, difference up here, in which case it can point in the opposite direction if that coefficient is negative. It will flip it, and in that case, if you did that, your determinant would be negative, right? You've now flipped an eigenvector, so your transformation is going across the boundary. Okay. Then we have theorem 4.8, where the lambda is an eigenvalue of A if and only if lambda is a root of the characteristic polynomial, right? So it's one of the things that gets this characteristic polynomial to be equal to 0. Okay? But again, we can see that because that is the value of lambda which gets A to drop rank. All right. And again, I like the perspective as well, where C0 is the determinant. So that's a non-zero value. And then you're picking these values of lambda here, such that the rest of this equation can undo that determinant. It can undo that stretch to a point now where I'm taking something that has volume and just making sure it has area. Okay, getting that area, that stretch back to 0. So there's a number of perspectives you can take. If you want to work the characteristic polynomial perspective of, you know, what I just said now, where you're starting with the determinant and then figuring out the lambdas to undo it, fine. If you want to consider actually that case where it's more in terms of what's happening to this box that I'm operating on, and I want to maintain volume or lose volume, then that's also okay. Or you can think of it in terms of this, where it's saying if I apply an operation to a vector x, if that is just the same as scaling x, then that's also an eigenvector. They're all equivalent, okay? And that's largely the point of saying this. Okay, these three things might look like they're all saying the same thing, but actually they're all very different interpretations. Okay, they're saying either I'm taking something with volume and getting it 0 volume, or either I'm scaling in a direction and there's no rotation in that direction with an operator, or it's saying I can't invert out of it. Okay, and I hope that's kind of what's starting to come through now as we get to this lecture and the kind of next lectures, is that a lot of the stuff we've gone through in the first 4 weeks with change of bases, orthogonality, inner products, they're all going to start coming together, and we're going to realize that a lot of those things have been repetitions with different perspectives of the same fundamental thing, which is I really care about vectors, I really care about what space they're embedded in, and I really care about what space they occupy in their own right. Okay. That's the whole point. And again, when you get to doing data science, that's the fundamental thing that you're going to be applying in your mind. You know what I'm saying? When you've collected 1 billion features from your clients and you're working at Liberty Life, but it turns out that thing is embedded in 2D. You know what I mean? And you can point that out to the CEO, that's where you make lots of money and everyone wants to work with you, right? Because now you recognize that there's only 2 factors of variation in your clientele. Even though, you know, you look at their heights and all the, you know, whatever other metrics of banking Liberty Life is looking at. Okay. And that ability to connect rank, ideas of rank and ideas of, you know, invertibility and those sorts of things to those tangible features in your data, that's again where value comes from. So I know this course at this moment is still very, I mean, I say still, it's only going to be like very theoretical in this way. But that should ideally be the outcome of this course, is that by understanding it geometrically, understanding it in terms of how to take the perspective of I have a cube, or I have lost volume so it's uninvertible back into a cube, you know, and I have a square that I can't expand or whatever. Hopefully those ideas come through when you start looking at data. Okay, and again, rank will tell you how many what's the actual space of variations of clients, even if it's embedded in R 10,000. All right. So lambda is an eigenvalue of A if and only if lambda is a root of the characteristic polynomial. We just said that. And then the algebraic multiplicity, we can define that as the number of times a particular eigenvalue shows up. So let a square matrix A have an eigenvalue lambda I. The algebraic multiplicity of lambda I is the number of times the root appears in the characteristic polynomial. Okay? It's the number of dimensions in our space that are stretched in the same magnitude. Right? That's what the algebraic multiplicity is telling us. In that sense, a square that lies along those eigenvectors will remain square. Okay? That's a little bit more of a niche point. I can't tell you like how, again, to map that onto an example of Liberty Life, but maybe a Liberty Life data scientist can, hopefully. But that's the idea. Algebraic multiplicity is the number of times an eigenvalue shows up. Okay, and as a result, we can define an eigenspace or an eigenspectrum. So for A, which is an n by n matrix, the set of all eigenvectors of A associated with an eigenvalue lambda spans a subspace of Rn. All right, and that is then called an eigenspace, and it's called the eigenspace of A with respect to lambda, and you denote it as E lambda. So again, everything that sits in this eigenspace of lambda, if it's square, it will stay square. You will maintain proportionality of those dimensions. Okay. The set of all eigenvalues of A is then called the eigenspectrum, or just the spectrum of A. Okay. This has some cool properties in machine learning. For example, you can tell whether or not a neural network will diverge based on the spectrum of its Hessian matrix. Hessian matrix is something we'll chat about. That's the matrix of second derivatives. It tells you about the curvature or the rate at which its derivative is changing at a particular point. And there's a really cool finding in machine learning at the moment. It's a bit dramatized, but they say that neural networks train at the edge of stability. So if you're in a linear regression, and again, we'll come to these points at some, in the coming weeks. But if you're in a linear regression, you can get to a single point. There's a single optima. So your loss landscape looks something like that if we're looking at it from top down. Okay, so I know there's a single point there. If you look at a simple neural network, and if any of you are supervising me for honors, it's something you might end up doing with me. If you look at a simple neural network, its loss landscape looks like this. And so what's happening here is that, at least my opinion of what's happening, is if you start at a point there and your Hessian curvature is too, you have a too large of a learning rate relative to the curvature of that Hessian, which will be told to you by its spectrum, right? So you can derive the maximal learning rate you're allowed based on that spectrum of the Hessian. If you go slightly over that in linear regression, you'll diverge. If you go slightly over that in a neural network, what happens is it does this. It will bounce around, and if you look at the kind of weights of your neural network, what they're doing is they will shake. It's almost like people have made the analogy to, like, if you have like rice or something in a pan and you shake it, the rice will diffuse across the kind of surface and become a lot more, like, your entropy will be maximized, right? Your rice is then as evenly distributed as possible at that point within, obviously the stochasticity in the world. That's the same idea. Is here what's almost happening is you're shaking your weights, and then they end up landing in the most entropic region in your space. But it keeps it stable, which is kind of cool. And there's a lot of research being done on, like, number one, that's a lot of people's belief at the moment of why neural networks train when they arguably shouldn't. There's a lot of statistical learning theory which says neural networks shouldn't work as well as they do. Some people believe that that's why. Anyway, if you want to nerd out with me about neural networks, we can do that later. But I hope at least you realize that some of the concepts we're doing in this course are very directly applicable to cool concepts in machine learning, if nothing else. Cool. That's essentially what I've written down here. So this eigenspace is just the union of all the eigenvectors, which share a lambda. And then if you take the union of all of your eigenspaces, you get to your kind of big ambient space. You should recover your original vector space. Cool. For a given value lambda of A, it is worth noting that the eigenspace for lambda is the solution space of the homogeneous system of linear equations, which you get from solving that. Okay, so again, this is, if you solve the determinant of that, you get the characteristic polynomial, but you can also do this by, and this is the way you usually will do this, you can solve this system of linear equations, right? We know that if this gives us 0, what's happened is we've found a setting of x, a line of x, such that such that it's lying in the null space of that matrix. Okay, and what that means is because we're in the null space of this matrix, the fact that it has a null space, okay, by the rank nullity theorem that we went through a couple of weeks ago, if you remember that, it says that the sum of the space that you start in, the sum of the space that you embed in and the sum of the space that gets left behind must be equal to the sum of the space you start in. If I start with a cube, I end up in a square, then the dimension of the space I got left behind was 1. I've lost 1 dimension. So it's 2 for a square plus the 1 dimension I got left behind was equal to the cube that I started in. Now, the fact that this has a null space means that you will find that x, number one, you'll find the x or the lambda that satisfy that equation, but it also means that you have successfully dropped rank. Okay, and if you remember, that is one of our definitions of eigendecomposition. All right. So in other words, what you're doing when you solve this system of linear equations, you will be finding the setting which will allow you to drop rank. Geometrically, the eigenvector then corresponds to a non-zero the eigenvector corresponds to a non-zero eigenvalue and points in a direction that is stretched by the linear mapping. We've gone through that. The eigenvalue is the factor by which it is stretched. If the eigenvalue is negative, then the direction of the stretching is flat. Okay, and so if you look at the case of the identity matrix, a simple but interesting case worth considering is that of the identity matrix. So if you take the determinant of the identity minus lambda times the identity, what you end up with is just factoring this out, and you get 1 minus lambda. Okay, you end up with, you pull the constant out, 1 minus lambda to the power of n, determinant of I, and then we know that that will kind of fall away. Okay, that'll give you a 1, and so you just end up with the determinant being 1 minus lambda raised to the power of n, again, because we're working with volume here, or we're working with, the number of dimensions that you're stretching in matters, because it's multiplicative. It's the volume for 3D, it's the area for 2D, and so now you end up just having to cube or whatever, raise to the power of the number of your dimensions. Okay. In order to find the eigenvalues, you then set this equal to 0, and so obviously there's just one solution to this. It's lambda is equal to 1. Okay. Does anyone want to hazard a guess what the algebraic multiplicity is? Correct. Who said that? Yeah, correct. N. All right. So lambda equals 1 is the solution to this equation n times. Okay. So moreover, the identity times x will equal to 1 times x. That holds for all of your vectors. This means that the E1, the vector subspace defined by your lambda equals 1, of the identity matrix spans n dimensions, and for all n standard basis vectors of Rn are eigenvectors of your identity matrix. Okay. In other words, what this means, if you're trying to be intuitive about it and link back to what I was saying earlier, the identity matrix is already a decoupled system. That's the main takeaway from this. Your eigenvectors will point in the direction of your canonical basis. And your canonical basis, again in 2D, it's 1, 0, 0, 1. Anything that's sitting in that basis, decoupled. I can move in the x direction or the y direction free. Okay, so if I'm doing dynamics in the canonical basis, I am free to treat them as individual 1D systems. Cool. That's the whole takeaway of that. Okay, and so some commonly used properties of eigenvalues and eigenvectors. A matrix A and its transpose A will have the same eigenvalues, but not necessarily the same eigenvectors. And then the eigenspace associated to a lambda is the null space of AI lambda, and we just spoke that through, right? This was our eigenvalue equation, right? So you take it over the sign, you factor out the x, and so now what you're doing is you're solving for the homogeneous system of equations, and we know that that's solving for the homogeneous system of equations. That's the same as finding a general solution, and so that gives us the kernel. Yeah, I was comfortable that you could do this. Comfortable with this. I'll show you an example of this at some point. Next lecture, we go through an example of eigendecomposition, just so that it's computable. Again, it's the kind of thing where learn the algorithms that you compute it, learn these definitions that you can understand it, and they don't have to happen at the same time. Just remember which perspectives to take when. Okay, and then lastly, some commonly used properties of the eigenvalues, eigenvectors again. So similar matrices possess the same eigenvalues. Okay, and again, I'm going to put you guys on the spot for a last time and take an awkward sip of water. What does that mean then about our eigenvectors? Okay, if the eigenvalues are the same, and we know that similar matrices will not, or change of bases will share the same singular values, or will share the same, how do I phrase this question? If they are performing the same stretch, right? If that determinant is the same, if they're the same matrices, what does that tell us about the eigenvalues?
Wouldn't they be the same?
Not necessarily the same. By definition, that's how you would solve for it. Okay. So you guys don't, I think, well enough. I posed the question badly. It means that those eigenvectors are acting as a change of basis. Okay. You're taking a space, and again, you're representing it in a basis that now you have a decoupled system. All right. That is the same perspective that you take here. All right. When I'm representing my system in terms of that basis defined by x, my eigenvalues, my eigenvectors, it is then the same. The equivalent transformation, or in this case, the similar transformation, because we're keeping our dimensions the same, is just a scaling. Okay? So it's almost by definition why this matters, is that it becomes a similar transformation, but that similar transformation is now completely decoupled, and the same as just scaling in those directions individually. And that's ultimately, in my opinion, why we should really, really care. Okay. So similar matrices possess the same eigenvalues, therefore a linear mapping has eigenvalues that are independent of the choice of basis of its transformation matrix. So we now have three key characteristic parameters of a matrix that are independent of the choice of basis: our eigenvalues, our determinants, and our trace. Okay? Symmetric positive definite matrices always have positive real eigenvalues. And this is also key because a covariance matrix just fits what I described. Okay? Covariance matrix is how you define Gaussians. You need to always define your covariance for a Gaussian. And so we know that in that case, we will always have positive real eigenvalues coming out of our data in that case. We'll get to that in a little bit, especially next time when we talk about singular value decomposition. All right. One other thing. Does anyone want to, again, I don't know how to phrase this question, but let's see how it goes. Does anyone want to tell me, in terms of the determinant of A, based on this slide and what's written on the slide, is there a way you can write A in terms of the eigenvalues? Yeah. Correct. There we go. We know for a fact that we can apply the determinants, we can apply those various properties of our determinant there. So we get D det of S inverse times the determinant of B times by the determinant of S. Okay, and I'm not going to write it out, but we know that those will cancel. Okay, so the determinant of A is going to be equal to the determinant of B. Again, it's invariant to the basis that we're using, whether or not we're in our original basis or our eigenbasis, they're going to stay the same. All right, but what that then ultimately means is because when we take the eigenbasis, what we've got is the equivalent transformation, which is doing scaling. What we end up with is just your eigenvalues along the diagonals. Okay, we know that the determinant of a triangular matrix is just the product of its diagonals. But in this case, we're going to have zeros on both sides. Doesn't really need to be, but that's a triangular matrix. That's both an upper and a lower triangular matrix because it's diagonal. And so now we know that the determinant will just be equal to the product of its diagonal. Okay, we'll cover that again next week. That links into the next set of slides. Cool. I think that's it for today. And obviously next week is a public holiday, so enjoy the break, and I'll see you when we get back to round out eigen decomposition, and then we end. If you give me 2 seconds, we end the kind of first block of this course after that. So I hope to finish eigen decomposition next time. And then linear algebra is done. We've covered all the geometric stuff that we're going to need for this course. And then from there, we move on to calculus and optimization, which I think is a little bit less definitions-y, a little bit less wordy, and a little bit more kind of obviously intuitive in terms of like optimization and things like that. So I know some people don't like linear algebra. That's coming to an end, but I hope next time as well, what happens is that we like kind of close the loop in a lot of these concepts we'll be doing. In particular, I really care about the idea that this is a change of basis. That's something I think is really important about these things. In particular, it's the change of basis that decouples your system. But again, we'll emphasize that again next time. No one has any questions? We can drop off. Guys online, you happy? Sweet. All right, thanks everyone.